out. What you rocking today? Oh, same things before?
Yeah, I'm putting at 30 days. I'm still letting it dry. Need some hot cool for
I get you. All right, so welcome. How was homecoming?
It was homecoming.
I've heard dumb, boring, trash. Yeah, that was generally the vibe that I got. You guys are all morons because you follow me on Instagram, and by me I mean my math account on Instagram. I think I've only posted 2 things so far, one of which was Shrek and the other was a marker. And you were even more dumb and allowed me to follow you back, right? Because again, clout for clout, right? That's what it's all about, right? I feel like I owe you, so I'm trying to do the right thing. So I followed you back, right? And then you accepted me. So I got to see all your homecoming pictures. Whoa, dear God, do I not want to see any of that? Yeah. Hey, Mr. Eads, how's it going? You had a good time. Yeah. So that was fun. But others of them were kind of like adorable. It was like, oh, my babies, they're growing up, right?
Hey, you didn't like my pose.
Nope. So anyway, yeah, and it's also fun seeing you guys hang out with people from other classes that I teach, and it's like, oh man, they're friends. That's crazy, because all I think of you is like you in here, right? And so when I see you with other people from other classes, a lot of the time I always look, and I look at 2 of you together, and I think, one of y'all could do better, right? I'm not gonna tell you which one it is. One of y'all could really do better. Yeah, sure.
What?
Some of you guys are batting out of your league, okay? But some of you guys, man, what are you doing? Jeez. All right. Anyway, I hope you had fun. Song of the day is "Super Stupid" by the band Funkadelic. Funkadelic is called Funkadelic because they are a funk band that also experiments with psychedelia. Stooges, you're upsetting people.
It's not Stooges if there's only 2 people.
It's not Stooges.
It's
not
just
being
dumber
funny.
and dumber.
That's right.
You're dumber.
There you go. We can debate about that in a second. But yeah, so song of the day is "Super Stupid" by Funkadelic. The band with George Clinton and the lead guitarist Eddie Hazel at this time. He's also lead singer for this song. Your warm up for today is going to be this. You're gonna hate me for it. First of all, here's your hint.
What? Infinity. How many squares do you guys see?
I want you to figure out how much of the total area of the square is taken up by the red, the green, and the yellow.
I'll wait for you to come.
I want you to give it a shot.
4.
That's as much zoomed in as I can get. I count 7 red squares here. It does go on to infinity. Let's just go to the first 5 squares. 1, 2, 3, 4, 5. Okay.
7. There's 6.
There's 6. There's 7 if you look really close. I mean, technically it's
That's
infinity.
a red one out there?
You what?
That's a red one out there? That tiny little...
Well, I mean, it keeps going. It keeps going. It's like this again and again and again.
Well, yeah.
Right?
What is the area?
Well, the area of the whole thing, we're going to call it X. Or 1 if you want, 1 by 1. I don't care. Best of luck. I'll be around to help. Song of the day, like I said, is "Super Stupid" and is dedicated to all of you. Just kidding. I have particular people in mind. Here we go. Oh, bad news. I think my sound card broke.
Oh, great.
Get that warm-up sheet. Why can't my shower at home be that nice? $12. keep going, right? Get this guy fired up. Eddie Hazel on vocals and guitar, and Funkadelic, super stupid. It's a song. Album is Maggot Brain, which you've seen the album cover for. It's the lady that's buried up to her neck and screaming. Maggot Brain, fantastic guitar solo by Eddie Hazel. I think I mentioned it before in here, but George Clinton, the band leader, told Eddie that he had just gotten off the phone with some people, and they said that his mom had died, right? And so Eddie goes in to record the solo for Maggot Brain right after hearing that. And he's like terribly distraught, right? So he heads in the studio, he grabs the guitar, and he just starts playing. And George Clinton is recording, right? He records this 10-minute guitar odyssey, just like mind-blowingly emotional, right? He's not Jimi Hendrix. He's not going to blow your mind with all his technique and just ridiculous stuff, right? He's not shredding, but like the emotion of this is so powerful. And then afterwards, George Clinton's like, J.K. Love, your mom's fine. But hey, we got a really good song out of it. 10-minute odyssey. Yeah, George Clinton, man. George Clinton. Eddie is dead. Most of them are now out of that band, but George Clinton's still alive and kicking it. Very large man. Can no longer stand up while he plays. Has to sit down and do it. But man, he can still like rock. I saw him last year, I think. Maybe 2 years ago. He's on tour again. He's going to be in Hammond, Indiana. I might go check him out. Sick. All right, anyway. How do we solve a problem like Maria?
Brandon, you didn't even write anything down.
Doc, what are you doing?
Name and draw the boxes.
Let's draw the boxes. All right, Doc. So we're going to start out with an easier problem, like you did up there on the board.
Yeah, see that easy.
Okay? Cut it in quarters. Something like that, right? I believe this was red, and this was green. We're getting very Rasta today. I have a sweatshirt with those colors.
Why?
What do you mean, why?
What makes it a sweatshirt in 3 colors? Like that's colors on the book.
All right, so
What's that?
these 3 colors. Fun fact, our eyes are only capable of seeing 3 colors, 2 of which are here. The other one is blue. We can't actually see yellow. Our brain interprets the mixture of certain colors as yellow. It's like the average between them. Same thing with pink. In fact, anything outside of red, green, and blue is just really our brain just like averaging them and coming up with an idea for it. Pretty bizarre, huh? Mantis shrimp can see over 9 different colors. Right? We can only see 3. So they have lots of different shades. They're funky looking dudes. They can also punch the water so fast that it actually makes the water around them evaporate.
That's what I was going to say. Is that when it comes to their brain?
Yeah. They have these boxing gloves, and it's so fast it's supersonic, and so it actually boils the water around them when they punch.
Hasn't been
Yeah.
science.
Science. And again, they also have this amazing vision. So anyway, here we go. And we know that this is a quarter of the whole thing, and that's a quarter, and that's a quarter, right? So if I divide this up again, well, this square is a quarter, right? Right, the whole thing right there. So I need a quarter of a quarter. Now when we say of in math, what we mean is multiplication. So a quarter of a quarter is multiplication. Now we multiply across with an A. 1 times 1 is a 1, 4 times 4 is 16. So this is a 16th. That makes sense, right? If I do crosses everywhere, I get 16 total boxes. That's 1 out of the 16. That's a 16th. And those are 16ths. Now, Doc, if I take a quarter of a 16th, because that square right there is a 16th, right? A quarter of a 16th is this. That's 1 in the top. 4 times 16 is 64. So now we got a 64th. Just keep getting smaller and smaller. It's this Russian doll situation. So we got more red, more green, more yellow. And if I cut that into a quarter, so take a 64th and cut it into a quarter, I've got a quarter of a 64th. that is going to be 1 over 256 for these guys. And we can keep going. I said we'd only do it out to 5. So let's do a quarter of 1, 2, I'm sorry, not 1, 2, 256. Quarter of that is going to be 1,024. Yeah. You can trust me on that. So now we're here. Something like that. Okay. So how can we figure out how much of the red area, or how much is taken up by the red? What should we do? Multiply them. Why multiply? So, Mr. Eads, when I did a quarter times a quarter, I got a 16th. What's smaller, a quarter or a 16th? Very good. So if I multiply a quarter by a 16th, I got a 64th. Which is smaller, a quarter or a 64th? Very good. So if I were to multiply all these together, I'm going to get a really small number. Why do we want a really small number? I'm going to get 1 out of... But isn't this already a quarter? Shouldn't I have more than a quarter if I have... You see what I'm saying? All right, I've already got a quarter filled in. So if I start filling in more, I should start having more than a quarter, right? So we can't multiply them. That's going to make them smaller. Simpler than that. What are we going to do? We're going to add them all up, right? Quarter plus a 16th plus a 64th, et cetera, et cetera, et cetera. Let's do that. All those added up. Now, question. Can I just add these up as they are, just straight across? No, otherwise I wouldn't be asking, right? Let's talk about that. Alex, you have a question? They don't have common denominators. Very good. So you know that because you've been told they have to have common denominators, and you happen to remember. We're going to talk about why that matters. So let's talk about these guys. A half plus 2/3. Now we know we multiply across, right? So what if we add across? Let's see what happens. What's 2 and 1 added together? What's 3 and 2? How do you know this isn't right? How do you know this can't equal 3/5? Explain to me. Why can't that equal 3/5? How do you know for sure it can't be? Somebody told me you're not allowed to do that. Well, what if they're wrong? Rule number 1 used to be on the board. It says trust no one. Yeah. How do you know that's wrong? This is the actual warm-up. The other one's just a distraction, and it's interesting. What I really want to know is how you think. That's been the gig since the beginning of the semester. You just didn't know it yet. But now you do. Alex, how do you know this is wrong?
Because simple form doesn't equal either.
Say it again?
Simplest form doesn't equal either 2/3 and a half.
I think I know what you mean. And not wrong, but not good enough. Not on the right track. I could be wrong about knowing what you mean, but I think you're on the wrong track. Come on. What does it mean? What does all this mean? Think about what it means. I know, you see fractions and you just lose your frickin' minds, right? Think about it. What does it mean? 2/3. 1/2. 3/5. Alex, try again. They're what?
They're close enough to a half.
Say it one more time.
They're all close enough to a half.
They're very close to a half, so that's exactly a half. Is 2/3 bigger or smaller than a half? Bigger. You'd rather have 2/3 of something than a half of something, right? Right. Cut up something in your mind in 3 pieces. You see what I'm saying? That's bigger. So we have bigger than a half plus a half, and we're getting 3/5. 3/5 is bigger than a half, but not by much, right? So we're getting something that's big, a half plus bigger than a half. We're getting barely a half. That can't be right. Right? This is going to be greater than 1. Take half of something, add 2/3 to it. Yeah, that's over 1. Right? So that can't be right. Not possible. That number is smaller than this guy. And we're adding it to it, right? We're adding something to it. It's got to be bigger than that. Can't be possible. Nice job, Alex. How do we do this? Well, we're talking apples to oranges here. We need to talk apples to apples. Anybody like that game? Apples to apples? I'm not a big fan either. I come up with some real good ones. My stupid, 6-year-old niece, right? She's not going to get that. It's right over her head. So what does she pick? The first one that's handed to her every single time. I hate that. So, 2/3 and a half. They got to talk apples to apples. What if we both put them as sixths? How many sixths are in a half? How many sixths are in a half? 3/6, right? 3 out of 6 is half. Just a different way of looking at it. How many sixths are in a third? Can you visualize it? 2, right? 2/6 in a third. 2/6 plus 2/6 plus 2/6, that's 6/6, right? 2 out of 6 is a third. So 2/6 and 1/3. How many sixths are in 2/3? 4. 2/6 and 1/3. So 4/6 and 2/3. In 1/3 there are 2/6. You follow me there? So now if I have 2/3, I have double that, right? 4/6. So really what we're doing is 4/6 plus 3/6. How many sixths do we have total now? 7. So we do add straight across. We just ignore the denominators. That's just telling us what we're talking about. It's like a unit, right? It's like saying I've got 4 chickens, you've got 3 chickens, now we have 7 chickens. 6 is the chickens. Okay? It's a unit. That's all. Cool. So, how do we get common denominators here? Oh. Greatest common factor? Busting out some, what was it? Was it TLAs? 3-letter acronym? It's an acronym for acronyms, yes. They're all going to have to be written as something over 1024. Right? The smallest piece is out of 1024. So all these guys have to be written like this. So let's start writing them like that. So one of these is just going to be 1, right? 1 out of 1024. Now check it out. To get from there to there, didn't we multiply by a 4th? Right? Yeah. Remember to get 256, we multiplied it by a 1/4, which is taking the bottom and multiplying it by 4. So there's 4 1024ths in 1 256. There's 4 of those. If you were to reduce that, you'd get 1 over 256. Both are divisible by 4. Going backwards. Now from here to here, we also multiplied by 4. So to get from here to here, I got to multiply by 4 twice. Now be careful, don't think you multiply by 8. I'm multiplying by 4 once, and then I'm going to multiply by 4 again. I'm multiplying by 16, aren't I? So instead of a 1 here, 16 out of 1024 is 1 out of 64. Now again, I got to multiply by 4 3 times. So 4 times 4 times 4. That's 64. So 64 out of 1024 is 1 out of 16. I did one of these too many. Last but not least, times 4 again. What is 64 times 4? Yeah, we already did it, didn't we? Right? It's 256. Use your resources. Now we got to add them all up. Well, it's going to equal something over 1024, right? Let's put the easy ones together. these two. What's 256 plus 4? 260. If I was a pro wrestler, that's what I'd weigh. 260. But I ain't. Mr. Eads! Let's put 16 and 64 together. Well, because it's not too bad. What's 64 and 6? What's 10 more? We'll try that again. What's 64 and 6?
80. Total is 80.
Thank you. So 64 and 6 is 70, plus 10 is 80, which is how much Mr. Eads weighs. And then we got to add the 1, right? You got it. Good job, Nate. So it's 341 out of 1024. Okay, what does that mean? Right? So what? Yeah, if we cut it into 1,024 pieces, that's true. But that doesn't mean anything to me because those numbers are so big. It's like when you say $10 billion, like no one really knows what that means, right? It's just like such a freaking big number, you can't even imagine it, right? Same thing here, it's just so many small pieces. So, would you say that the amount of red is the same as the amount of green, the same as the amount of yellow? So if I take something, and I cut it into 3 equal pieces, the same amount of red, the same amount of green, the same amount of yellow, how much are each of those pieces worth? A third. So all that should add up to a third. Now, the question is this equal to a third? Get out your calculator if you have one. And if you don't, no big deal. 341 divided by 1024. Doc's on it. Nate's on it. Nate, that's a nice pencil pouch you got there. Dope stuff. Cooler than mine. 341 divided by 1024. Is that a third? In other words, we're looking for 0.3 repeating here. Read it to me. How many threes? 3 threes.
2 zeros.
Two-
7, 8, and 1, 8.
Oh, and then a 3? Or 1 3?
1,
Okay. Enough! So, a third is equal to 0.3 repeating, right? This guy's really close, but he ain't. So riddle me this. Should be a third, and a third, right? It's 3 equal pieces, right? Same number of red squares, same number of green squares, same number of yellow squares. Why is it not a third? Or is it? Maybe we goofed.
I think it's 341.
I gave you a hint earlier. Alex. And how many colors do we have? Ladies and gentlemen, if I'm to take a square, and I cut it into quarters, and I color these guys in, right? And I do it again. What do you notice? Always 1 square left over, right? Which I then have to cut up even more. But there's always going to be 1 square left over. And I just had to keep cutting it up. And the more we cut it up, the more times we cut this up, the more adding we do, the closer we're going to get to actually 0.3 repeating, a third. It has to go to infinity. It's never going to actually get there. There's always going to be 1 square left over. But if we keep going to infinity, it will get to a third. The sooner we cut it off, the less close we are, right? If we cut it off here, each one of these is a quarter, right? So we get a quarter. If we cut it off here, we get a quarter plus a 16th. That's going to be 5/16. It's getting closer to a third. If I cut it off after doing this, we get even closer to a third. right? It's approaching a third. The further we go into infinity, the further we go down this rabbit hole, the closer the answer is actually going to be a third. Because it is. But we stopped only after 5 squares, right? Let's see if it gets closer. Let's do square 6 and square 7. Trust me, there's a payoff here. Think you're going to enjoy it. Think you're going to like it. I guarantee it. So we had a quarter, plus a 16th, plus a 64th, plus a 256th, plus a 1024. What's a quarter of 1024? Well, we multiply that by 4. Let's do it in our heads. What's 1,000 times 4? 4,000. What's 24 times 4? Easier question, what's 20 times 4? 20 times 4. 80. Now, I need to do 24 times 4. I only did 20 times 4. So how many more groups of 4 do I need? 4 more, which is 16. So 1,000 groups of 4. What's 4,000? 24 groups of 4 was 96. So that's going to get us 4096. Okay? 1,000 times 4, 20 times 4, 4 times 4. Add them all up. Let's multiply this times 4. What's 4,000 times 4? What's that? 16,000, right? 96 times 4. I'm going to round up. What's 96 rounded up? Hundo. Now that's too much, right? I'm not going to add on 400. I want to add on 96 times 4. So how many groups of 4 did I overshoot by? 4. I did 4 groups too many, so I need to subtract 4 times 4. Minus 16. You see what I'm saying? What's 400 minus 10? 390. Subtract 6 more. 384. So it's 16,384. All right, so it's 7 places, right? Let's get common denominators. They're all going to be over what? 384. Mr. McCartney, it's going to blow your mind. I did this just for you, buddy. I was gonna stop at 5, but I think we would miss something spectacular if we did. Well, one of these is going to be 1 over 16,384. I multiply this times by 4, right? To get to there. That's how I did it. So that guy's 4. I multiplied this guy by 4 to get here, and then 4 there. So I multiplied by 16. 4 times 4 times 4 to get there. That's 64. 2, 5, 6, 10, 24. And last but not least, I multiply that guy by 4. And I'm going to get 4,096. Let's add them all up. This reads. Which 2 do you want to add together? 2, 5, 6, and 4. What do those get us? 260. That's what I'd weigh if I was a pro wrestler. Mr. Eads, which ones do you want to add up? Say it again. You get 65? All right, suit yourself. Ivy, which ones do you want to add up?
I don't know.
Not a lot of good choices left, but they're okay. These 2? If I was doing it, I'd either do these 2 or these 2. Ivy, which one do you want? Okay, so it's going to be 1,000 something, right? 16 and 24, let's do 10 and 24. What's that? 10 and 24. Add them up. Nope, 34, right? 10 and 24? Yeah, it's all good. You're thinking too hard. It's okay. Don't worry about it. You add on 10, you get 34, right? Well, we got to add 6 more to that. 34 plus 6. Yeah. So it's 1040. Big 10-4. My truck stop friends. Shout out to them. Hope they're watching. Breaker, breaker. Oh, let's add all these up. I'm going to put these two together. When I put these two together, I get 1, 3, 6, 5. I add these two together, I'm going to get 5, 3, 6, 1. So we have 5,361 over 16,384. Is that a third?
Yes.
Plug it in your calculator.
Yes.
It's really close. It's not perfect, right? Because we did stop before hitting infinity. So it's going to be really close. Question. Is this in simplest form? It's not. There's a number that almost goes into it. We would check them all. I'm cutting to the chase here. And we get to a number that's really close. 13. Mr. McCartney, if you would do the honors. Let's divide both these numbers by 13. Would you divide 5,361 by 13?
That's 412.
Try that again. Divided by 13. 5,361. Let me make sure I didn't add up something incorrectly along the way. Oh no! The magic trick. I have all my notes back there. Let me make sure I added these up correctly in my head. 5, 11, 1, 7, 11. What'd you get? My bad. 5, 4, 6, 1 divided by 13. Gentlemen, you're going to miss the payoff. 5, 4, 6, 1 divided by 13. So it's 420 and change. It's actually remainder 1 left over. So 13 almost goes into it. Close but no cigar. What are you talking about? I have no idea what you're talking about. I have no idea what you're talking about. It's a third. Put it away. Today, what I want to do is pass out a little worky sheet packet thingy to you. Why? Why?
Better than doing the corn with old players.
Oh! There you go. He's not a fan of warm-up. He's not a thing. He's not a big fan of the whole thing.
Too soft, can't process it.
Whoa there, old dog. Yeah, relax. We're just training.
Mr. McCartney is here today. We need to respect his decision to be here.
Yeah, right. This is not bad.
Hey, I'll be honest. I love having him here. Really do. I really do.
Don't get me started coming up.
What can I do to help you be here more often? Seriously, name it. Do I need to drive your house, pick you up? What do I need to do?
How? I don't know how.
Wake up call in the morning?
Yes, we'll wake up and fail. It was water. It was water.
Seriously, like, don't leave me here with these people. All right, so check it out. Talking about transversals, angles, parallel lines, all that jazz. Okay, we've talked about it before. Below the objectives, it says corresponding angles, alternate interior angles, alternate exterior angles. We know what these things are. Mr. McCartney may or may not have been here, though. So what I'm talking about, interior, I'm talking about the inside, right? That's the interior. All right, so interior angles, 3, 4, 5, and 6. They're all interior. When I talk about the exterior, I'm talking about the outside. So like 1 and 2 are examples of exterior angles, but also so are 7 and 8, right? Now, this word alternate that we're seeing here, it's talking about being on opposite sides of the transversal. So that line that's cutting the two others, we call that a transversal, right? And so we have opposite sides of the transversal. So we have the left side and the right side. So alternate angles would be like 1 and 2 because they're on opposite sides of the transversal. Alternate interior angles would be angles that are in the interior and on alternate sides. So like 4 and 6. Cool. That's all. So alternate exterior would be like 1 and 7. alternate, different sides, exterior, both on the outside. Now we have same side as well, right? Which means they're on the same dumb side. So like 1 and 5 are same side, right? Also, corresponding angles. An example of corresponding angles would be like 1 and 5. They correspond because if you look at the intersection, that's top left corner, right? See this intersection? Top left corner. Corresponding angles postulate, CAP for short, says that if you have two parallel lines being cut by a transversal, which we do, then the corresponding angles are going to be congruent. So 1 and 5 are the same. 2 and 6 are the same. 4 and 8 are the same. 3 and 7 are the same. Okay? Only true when they're parallel. If they're not parallel and we have something like this, right? Here's my transversal. It's cutting both of them. Right? Here's an intersection. Here's top left. Here's an intersection. Well, actually, I guess we'll call it top right. Those aren't going to be equal. Right? It's because those two lines aren't parallel. Right? So it's only the magic only happens when they're parallel. It says consecutive interior angles are supplementary. So what it means by that, same side interior. Cross that out. Same side. So these guys, 4 and 5 are same side and in the interior. They're supplementary. They add up to 180. We know this. All right, example. In the figure below, measure of angle 2 is 75. Let's write that in. It's easier to see. Angle 2 is 75 degrees. Find the measure of the remaining angles. Okay. What's the measure of angle 1? Corinne, how was homecoming? Yeah. Gets kind of old.
There to take pictures and go to dinner.
Gotcha. Was dinner good?
I should have went for the dinner.
Where'd you go?
Candlelight.
Nice. I've heard good things. Yeah. 115? Not 115. 105. Because they have to add up to 180, right? Angle 1 and angle 2 are a linear pair. See how that's 180? You seen it now? Okay. See how they both sit on a line? So they both are on a line. There's two of them. We call that a linear pair. A line is a straight angle. Straight angles are 180. So if that guy's 75, that guy has to be 105. I'm glad you mentioned that. Trying to catch you up to speed here. Please tell me if you're lost. Usually it's something small like that. It's really easy to fix, right? But if I don't tell you,
3 would be 105 too.
has to be. Now, how did you know that? Mr. McCartney has not been here to learn, but he is inferring. He is using his brain.
He's been watching you on YouTube.
Oh, maybe he has. Like and subscribe. Leave that comment, man, so I know you're there. All right, so I doubt that's the case. He knows that, oh, look, 2 and 3 are also a linear pair. They're sitting on a line. So they have to add up to 180 as well, so that guy has to be 105. Right. We have another theorem for that, Mr. McCartney. Would somebody like to explain this to him? Scissor theorem. Your words, not mine. Okay? So check it out. If I have two lines intersecting, doesn't matter how they intersect, notice the top angle and bottom angle are always the same. Right? See how they're always the same? Same thing with the side angles. Real big, real small, like they match. This is kind of hard to tell because it's got a bend in it. But anyway, we call this scissor theorem. It's really vertical angles theorem. Vertical meaning up and down. These two match, right? Also these two do. But they call it scissor theorem. I'm not sure why. I think it has something to do with the angles scissoring each other. Like there and there. That's what Tucker said. All right. So these are both 105 by vertical angles theorem. Or you could do what you're doing, improving vertical angles theorem. Well, they have to be 105 because they're a linear pair. Remember, a theorem is provable. So I know those are the same by vertical angles theorem. It's like a shortcut, right? But if you didn't know that, like Mr. McCartney didn't, you can go, oh, well, that has to be 105 because these are a linear pair. These are always going to be the same. You just invented vertical angles theorem. Scissor theorem, Mr. McCartney. You may call it what you wish. So what do we know about angle 4? It's also going to be 75, right? Either because those two are a linear pair, right? Or vertical angles theorem. What have you, right? All right, Mr. McCartney. Brain buster. This is where you're going to get stuck, and that's okay. What do we know about angle 7?
105.
How?
Alternate X.
They are alternate exterior, but we don't have a theorem that says alternate exterior angles are equal. Alex. Corresponding. So check it out, Mr. McCartney. The simplest one is corresponding angles postulate, okay? That's like the thing it all stems from. Corresponding angles are 3 and 7. They're both bottom right corner. Remember, corresponding angles postulate says if they're parallel, which they is, then these guys are always going to be the same. So 3 and 7 are the same, 2 and 6 are the same, 1 and 5, 4 and 8. Okay? So that means angle 6, 75. Angle 4, 75. Angle 5, 105. Again, if you get one of them, you get all the rest for free, right? Vertical angle / linear pair. So things we used here were linear pair theorem. So Mr. McCartney was using, saying two angles add up to 180, right? If they're a linear pair. And then we also use vertical angles a little bit. And we also use, what's the corresponding one? Cap. Corresponding angles. Postulate. Remember, postulates aren't provable. It just is, man. They just is. I like them apples. Turn the page, Mr. Eads. Example. In this figure, angle 3 is 102. Find the measure of each angle. Tell us which postulates or theorems you used. So it's the same dumb crap as before, just with an extra line. And then they want you to tell which postulates or theorems you use, which I just did on the last one just because I felt like. So they tell you 3 is 102. Mr. Eads, do you like that I gave you the homework early?
Yeah, come on now.
Yep. Mr. Eads, let's fill in the rest. If we know angle 3 is 102, what else do we know?
I can't see it. You know, 1 is 102, you know, 9 is 102, you know, 11 is 102, you know, 5 is 102, you know, 7 is 102.
Did you say 9, 11?
No, I did not. I said 11, 9. You know, 5 is 7.
We're going to go back in the film. He definitely said 9, 11.
13 is 15.
Mr. Eads, wonderful.
Then the rest are 7.
How do you know those are all 102? How do you know 1 and 3 are both 102? We got 3 for free, right? Scissor theorem, vertical angles. Your words, not mine. How do we know 9 is 102? Corresponding. 1 and 9. Nice job. How do we know about 11? 11. Scissor theorem, right? How do we know about 13? Corresponding between which two angles? Which two angles are corresponding? 13 and 1? 9 and 13, yeah, I mean, I would take 13 and 1. But 9 and 13 is a better answer, right? They're both top left on this side. Same thing for the rest of them, right? Corresponding angles, vertical angles. How did you know these two were vertical angles? These ones right here. No, they're vertical angles. They're across from each other. Which two angles here are vertical?
11, 9.
Gotcha. That's my fault. I butchered it. I butchered it. I butchered it.
Would 14 be 78?
Yep, that's right. By linear pair theorem, right? They have to add up to 180. So those are all 78. 78, 78, 78, 78, 78, 78. All right, so angle 5. We know it's 102. How do we know it's 102? We know 3 gets us 1, so that's vertical angles, right? So we use that. And then we did, from there, we did corresponding, right? Now, if you're clever, you might have done alternate interior angles theorem. 3 and 5 are alternate interior angles. So you could have also done alternate interior angles. I want you to finish up this example and the practice for tomorrow, okay? Those two. Nah, I don't do all of them. Just this page. Fantastic. Fantastic. That's the deal. Sit down, Eads.
I'll sit in my home for you.
There's 2 ways to do it. You could either walk yourself through kind of slowly and be like, look, I got that for free, right? That's vertical. And then these two are corresponding, right? Or you could just say alternate interior angles. 3 and 5 are the same because they're alternate interior. We have a theorem that says those are always going to be the same if those guys are parallel, which they is. Heck yeah. Mr. McCartney.
I might not be here tomorrow, but I'm at work.
Okay. How's that going to go?
I don't want to publish in the court work usual.
Cool. All right. Well,
I'll be here every day.
there you go. Because you've been missing because of court, right? No. Oh, gotcha. All right. We got that on tape. I won't turn that in. Don't worry. Later.
Have a good day.
Hey, you too, man. Love you, brother. What's up?